Hello, this is lecture 12B for Calculus 1, the area under the curve function and the fundamental theorem of calculus. My name is Scott Grizzard from the University of South Florida. So we're going to look at the module 4, which is integration, but we're going to start with something a little bit different than you've seen in pretty much any presentation in the book. Because what we want to do is we want to emphasize the idea that this area under the curve is a function. It moves. That's slightly different than the static version that the book is going to give us. So there's nothing wrong with that, except you miss something in that presentation. When you talk about the derivative, if you talk about area under the curve as something fixed, we want to think about it as a moving function. So here's our motivating thought. Okay, so what we're going to talk about is the area under the curve function, the properties of this AUC thing, and then the fundamental theorem of calculus. Then here's our motivating thought. The area of a circle is pi r squared. The circumference is 2 pi r. So if I take the derivative of my area, I get my boundary, my circumference. Why? Strange. What is it with this area function? Okay. So let's talk about what it is. So what I'm going to do is I'm going to take a curve here. In this case, I'm going to take 1 plus cosine of x. And then what I'm going to do is I'm going to map out the area between the curve, this is the curve, and the x-axis as I move from left to right across the screen. So here, I'm starting at 0. 0 is my base point. And you'll notice that f of 0 is 2. But I've not, from the area under the curve, from the base point 0 to the top point 0 is 0, right? I've got no width. So as I hit play, you can see me start to accumulate area as I move to the right. So here, x is 1. So f of 1 is about 1.54, blah, 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 blah. But the area I've accumulated is 1.84. So that's the shaded green region. So this is the area under the curve from 0 to x equals 1. And I've got this kind of shaded region here. And I'm measuring that area. As I hit play here, see, I'm measuring more and more area. I'm adding area as I go on. And because this is always above the x-axis, my area under the curve is always getting more, right? I'm accumulating more area. So if I stop here from f of 7.2, right, 1.6, but area under the curve. So under the curve, between the x-axis and the curve, I've accumulated 7.99. When I get to 7.2, I've accumulated 7.99 green shaded area region. And I just keep hitting play, and you'll notice that I'm accumulating more and more area as I go to the right. So that's the big idea behind area under the curve. It's as I move to the right, I accumulate area from my base point. In this case, my base point was 0. Okay, let's look at another example of this. Here, I'm going to accumulate area from the log of x plus 1. But my base point is going to be 1 in this case. So when I start accumulating area, notice that I'm accumulating area starting from 1, not 0, but 1. So that's my base point. And then as I move to the right, I accumulate more and more area. Okay. Now, if I am above the x-axis, I'm going to accumulate positive area. But if I'm below the x-axis, I'm going to accumulate negative area. So again, here's our function, and my base point again is at 0. And I hit play here, and I'm accumulating positive area until I get to 2. And at 2, the function goes under the x-axis. So now, as I move to the right, I'm going to accumulate negative area. So as you can see, I'm accumulating negative area as I move to the right. So that's this function. As I'm moving from left to right, if x is right of the base point, if I'm above the axis, I'm accumulating positive area. And if I'm below the axis, I'm accumulating negative area. Okay? So as you can see here, this area under the curve function, when I get to 4, I've actually, ignore this little weird artifact. That's just an artifact from the way that I programmed this. Here, when I'm under the curve here, I've accumulated negative area. Okay? So if I go here, I'm accumulating positive, positive, positive. I'm getting bigger. Now I start accumulating negative area, which starts to offset my positive area. And then at the end, my area overall is negative because I've got more negative area than positive area. So that's the big idea here. Okay? So what we're going to do, let's talk about this. Okay? Here's f of x equals 1/2 x. And my base point is going to be 0. Now, I want to compute the area under the curve here if I go to something in particular. So this is easier. This is a triangle, and I chose a triangle for a reason so that you could actually figure it out. So let's figure out what the area under the curve is if I go to 1. Okay, so I want this shaded region. What I want is the area under the curve of f, which is 1/2 of x, from the base point 0 to an x of 1. Okay. So how do I compute that? Well, it is a triangle in this case, right? I chose 1/2 x because it's a line. So this one is a triangle. So I can actually figure that out, right? It's 1/2 base times height. So my base is 1. And my height is 0.5. So if the area under the curve from 0 to 1, in this case, is 1/4. And if I look at my animation for that, right, here's that function again. Let's hit play here. Oops. As you can see, when I get to 1, I've accumulated 1/4 worth of area. Okay. All right, so let's look. What is it when I get to 2? Well, if I get to 2, oops, went too far again. If I go to 2, I should have accumulated 1 area. And then we'll see that if we go flip back here. So my area under the curve, and so now I'm going to do 1/2 the base, which is 2, times the height, which is 1. And that's how I got the area under the curve from 0 to 2 equals 1. Well, I could do this again and again, right? 1/2 base times height. It's kind of easy to solve for. So if I go up here to 6, oops. If I run it up to 6, I'll wind up with 9. I could keep going forward. Right, here's 7.2. There's 7. Right, there's 8. That's what I programmed in here. So that's the area under the curve. Okay, it measures the area between the curve and the x-axis from the base point to my current x. So here my current x would be, 2.9. Then the area that's been accumulated from 0 to this point is 2.1025, blah, 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 blah. And this is something that moves. So I want you to think about this area under the curve as a function that's moving. All right, so how could I solve this for, in general? Well, for this particular function. Well, for this particular function, let's say I start at 0 and I want to go to x. So my base point, so it's going to be 1/2 my base, which is x, times my height, which is f of x. Okay, so x squared over 4 is this area under the curve function. That will actually measure this area. So if I take it to, say, if I take it to 4, so I do x squared over 4, well, that would be 16 over 4, and that's 4. And that gives me the area under the curve here. Okay, well, that's interesting. By the way, what's the derivative of this? Well, I'm going to get 2x over 4, which is the same thing as x over 2. Wait a minute, that's my original f. So the derivative of this AUC function here was actually just x over 2, which was f of x. That's interesting. Okay, well, let's see. What happens if I change the base point? So now, instead of a base point of 0, I'm going to have a base point of 1. Okay, so when I hit play, we're starting with a base point of 1. So I'm going to hit play here, and I'm going to go do 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 do. Okay, so when I hit 1, right, how do I compute this big triangle? Well, this area here. Right, well, I want to compute this thing here. One way to do it would be to compute the area all the way from 0 and then subtract this little area here. Okay, so let's see how that would be. So let's say I want to compute from a equals 1. Let's say I want x to equal 2. So what I'm going to do, in order to compute this for x equals 2, I'm going to compute this area here, and then I'm going to subtract that area there. Okay. So that's going to be AUCF1, my base point, of 2, is going to equal, well, let's do 1/2 times the base, which is 2, times height, which is 1, minus this little bit right here, which would be 1/2 base, which is 1, times height, which is 1/2 again. So that's good. Those are going to cancel. I'm going to wind up with 1 minus 1/4, which equals 3/4. So if I travel from 1 to 2 on this and measure the area that was covered, I wind up with 0.75. So that's the area under the curve here from 1 to 2. Okay, that's interesting. Well, what happens if I want to do in general on this one? So what happens if I want to do the general, right? I want a general x. So we've got, I'm still going to be subtracting that same little bit. So it's going to be AUC F1 of x is going to equal 1/2 base times height minus the area of that little bit. Okay, so that's going to be 1/2 x times 1/2 x, because 1/2 x is f of x, minus 1/4, which is going to equal x squared over 4 minus 4. So that's AUC F1 of x. Notice that notice two things. This is actually equal to AUC F0 of x minus AUC F1 AUC F0 of 1. So I've got a kind of a change of base point formula, so to speak. And then let's take the derivative of this. And again, we find our derivative of our AUC function is simply what f was, which was x over 2. That's interesting. Okay, notice another thing here. If I take this down, if I let AUC f1 of x, right, this is the exact same formula I had before. If I take this formula down, x squared over 4 minus 4, I'm sorry, that should be x squared minus 1/4. So if I take this formula, x squared over 4 minus 1/4, okay, and I plug in 0, I should wind up with negative 1 over 4. So I'm going to have negative area if I go to the left. Okay? So if my x is left of my base point, I'm going to wind up with negative area. So here's that whole function again with the base point of 1. And so here here's that whole function again with a base point of 1. Right? And here I have no width, right? Because I'm at 1. But if I go to the left, if I start from the left, if I start at 0, AUC F1 of 0 is negative 1/4. I've got negative area because I'm left of the base point, right? 0 is left of 1. But then as I hit play, what's going to happen? When I hit play, I start eating up that negative area as I move back toward the base point. And then, of course, I'm positive again, and I'm gaining positive area. Okay. Well, let's say here I'm going to let the base point be negative 4. Okay. So let's rewind this, not that one. Let's rewind this one all the way. I'm starting at negative 4. Now I'm under the curve. So when I hit play here, from under the curve, I'm going to accumulate negative area until I get to the 0, and then I start accumulating positive area. Well, that means that if I'm left on my base point, but negative, so I'm left but under the curve, I'm actually going to have positive area that I'm going to be losing as I move to the right. And then I'm going to have positive area when I hit the 0, but now I'm over the curve and to the right of the base point. You can see this more clearly if I move the base point into the negative area. So here, the base point is negative 1. Right now, x is negative 4. And as I move to the right, I'm going to eat this positive area until I get to negative 1. But since I'm below the x-axis, once I move to the right, I'm going to have negative area until I get to 0. So right now I'm eating positive area. There's my base point, and now I'm adding negative area, and now I'm adding positive area again. So the rules for this thing are if x is right of a and f of x is greater than 0, I'm sweeping out positive area. If x is right of a and I'm under the axis, area sweeping out will be negative. And if I'm left and above, it's negative. And if I'm left but below, it's positive. Okay. Well, let's look at some of these properties of the area under the curve. The first is that this move of base point formula. I've got this kind of weird formula where I could change the base point. That's what we did here, where I kind of took the positive area And then I subtracted this area right here in order to get the area from 1 to 2. So I have that change of base point formula. Another interesting thing is that if I flip my base point and my x, right? If I flip, so if A is the base point and B is the function, if I flip those things, I simply get a negative. So if I flip the base point and the endpoint, I simply get negative of what I had. Now, I'm going to make the following claim. I'm going to make the claim that I could have taken any g whose derivative is f and compute AUC FA of x by simply taking g of x minus g of a. So g of x, x squared over 4, that means g prime of x was x over 2, that's f. So I claim that AUC FA of x equals g of x minus g of a. So that would give me x squared over 4 minus a squared over 4. Or the area under the curve of f from 1 to x would equal x squared over 4 minus 1 over 4, which is what we found. That's interesting. That's going to give us the fundamental theorem of calculus. Is this important? Let's see. This course is called Calculus, and this theorem is called the fundamental theorem of calculus. Yes. We're going to let D be an interval, A and D, and F defined on D. If F is continuous and G is a function so that G prime equals F, then two things are true. The derivative of the area under the curve function is F, and the area under the curve function from a to x is g of x minus g of a. This g is called an antiderivative, which will be the subject of part 1 of next time's lecture. And it's a very interesting thing. And this is how we can actually compute the area under the curves. Now, everyone's going, well, what? Don't you just need integral notation? No. I don't want you to use integral notation yet. If you know what that is, I want you to try this notation because the emphasis for this is on FDC1. If you view everything as static, the emphasis is on FCT2. But we don't want to do that. We want the action to be in the X because that's what's moving. Okay? So use this interesting notation. It's a medical school notation. If you're going to medical school, you'll see it again, except in medical school, they usually capitalize it as capital A, capital U, and capital C. But it's area under the curve, and it's important. Okay, so as I said, this notation, we won't see it again unless you, right, the integral has several notations, just like the derivative does, but you usually won't see the this notation unless you go to medical school. Okay, or do some chemistry with pharmacokinetics, because that's who uses this stuff. Okay, so what I want to do is I want to think about real fast what this means. So if I go back to this first bit, the derivative of the area under the curve. So let's go back to our screen here and look at this. Now, here I've got positive area, right? Right now, my base point is 0. And I'm left of my base point at -2. So I'm left under, I've got positive area. But notice what happens when I hit play. I'm taking away positive area. As I move to the right, I take away positive area. So the change is negative, right? The change in my area under the curve is negative. Here I had 4 as my area under the curve. I hit play and I'm losing area. Because I'm moving toward the base point. F is below the x-axis, so this is positive area, but I'm taking it away as I move to the right. So my change is actually negative. Now, I'm above the x-axis, left of the base point, I'm taking away negative area. So my AUC function is actually getting bigger because right now it's -0.8 or more positive. Because right now it's negative 9.8. I hit play again, and now I'm at negative 6.65, right? So I'm less negative. I'm more positive. Now I hit play again. Now F is above the axis, but right at the base point. That means I'm accumulating area, right? Positive area. So now my derivative of area under the curve is positive. And now I keep moving, and now I'm accumulating negative area. So I can view AUC as something just, remember we had this idea in module 3. I can think of AUC as the function that would go on top. If this is F and this is F prime, I can think of AUC just sticking on here. Because when F is positive, AUC is going to be increasing. When F is increasing, AUC is concave up. When F is decreasing, when F is negative, AUC is decreasing, right? Because I'm either taking away positive area if I was left, or I'm adding negative area. And here, if F is decreasing, AUC is concave down. Okay? So that's kind of an interesting thing. All right. Okay, so that's kind of an interesting way to think about it. We're going to think about this some more. And next time, what we're going to do is we're going to talk about antiderivatives. And then we're going to also talk about, there'll be 2 lectures next time. There'll be a part 1 and a part 2. So what are the big ideas of this lecture? Were that of what this area under the curve was, and then the fundamental theorem of, that it's a moving thing, and then the fundamental theorem of calculus. And this will be on every quiz from now until, well, not on the quiz that I ask you how you did on the test, but on every quiz left, this is going to be a question. State the fundamental theorem of calculus. It's that important. And what we're going to be moving toward is proving it. And that's going to be kind of one of the last things we do is prove the fundamental theorem of calculus. But we're going to use it before we prove it. So next time I'm going to talk about antiderivatives, and I'm going to talk about the min and max functions, which is just something we have to pick up before we can talk. We can give a better definition of this. So that's what I have for you today. Have a good one.